Hi everyone! For today's video, we will be discussing about a specific lesson in graph theory, the Eularian and Hamiltonian paths. Now, let us start with Eularian paths. Back in 1735, a Swiss mathematician named Leonhard Euler solved the Königsberg bridge problem, which started the history of graph theory. The bridge problem involved the possibility of finding a path in order to walk through the whole town of Königsberg that had two islands and seven bridges without ever crossing a bridge twice. Euler stated that there was no such thing possible, that marked a theorem in graph theory named after him called the Eularian path. A Eularian path means that it is a path that uses every edge or line that connects the vertices in a graph only once. In simpler terms, you can create a path in a graph whichever vertex you want to start off and use all the edges in the graph. But the catch is you cannot repeat the same edge to cross all the edges. And since it is a path, it does not need to return or end in the same vertex that they started. Just a heads up, vertices are points or nodes in a graph, while edges are those lines that interconnect the vertices to other vertices. Now, going back, to further understand, let's take a look at the graph. In this graph, there are several paths existing. One example of which is the path V, Y, Z, V, W, X, Y. Another one would be V, Y, X, W, V, Z, Y. If you would look at the examples closely, you would notice that all the edges are used. Some of the vertices were repeated, but not the edges. Also, it started and ended on different vertices. This is what you call a Eularian path. Now, is there such a path that can start and end on the same vertex? Yes, there is a path that exists, but this is rather called a Eularian circuit. Just like the Eularian path, it has a restriction of using an edge only once, but since it is a circuit, it must start and end on the same vertex. Take a look at the next example. A Eularian circuit that exists here is Z, Y, X, W, V, X, Z. Another would be X, Z, Y, X, W, V, X. Notice that it used all the edges, but none are repeated, and it started and ended with the same vertex. Now, without breaking a sweat and list and think of all the possible paths of a graph, whether it has Eularian paths or circuit, there are such theorems that are needed to follow. For a Eularian path, the theorem is that a graph will contain an Eularian path if it contains at most three vertices of one degree. Degrees are calculated by counting the number of edges that is connected with the other vertices. Going back to the first example, the vertex Z has 2 degrees, Y has 3, X has 2, W has 2, and lastly, V has 3. In accordance with the theorem provided, the graph has two vertices that have an odd degree, which are Y and V, making the graph a Eularian path. On the other hand, the second theorem discusses that the graph will contain a Eularian circuit if all vertices have even degree. Examining the second example, vertex Z has 2 degrees, Y also has 2 degrees, X has 4, W has 2, and lastly, V has 2 degrees as well. This satisfies the second theorem since all the vertices have degrees that are even. Therefore, the graph is a Eularian circuit. The importance of the Eularian paths and circuits is actually essential in our everyday life, some of which is essential to many careers in finding a route that they will not go back to their previous step or route, and to the DNA fragment assembly and many more. Moving on, the Hamiltonian path will be discussed. This path in graph theory was first used by William Rowan Hamilton in 1857. He actually invented a puzzle game which mainly involved finding a special path that was later known as the Hamiltonian circuit. But the Eularian paths and circuits The Hamiltonian graphs also have what we call Hamiltonian paths and Hamiltonian circuits. The Hamiltonian path uses all the vertices in a graph, but the vertices should not be repeated and it does not need to have the same vertex for its starting and ending point. Meanwhile, a Hamiltonian circuit uses all the vertices in a graph with no repeated vertices, and since it's called a circuit, it must start and end at the same vertex. An example of a Hamiltonian path is Z, Y, X, W, B. Another one would be Z, X, Y, W, B. Notice that all vertices are covered in these while not repeating them. Also, the graph shows a Hamiltonian circuit with V, Y, W, X, Z, B. All of the vertices were used without repeats but started and ended with the same vertex. Moreover, just like with the Eularian path, the Hamiltonian path has theorems to determine if such graph has a Hamiltonian path or a Hamiltonian circuit. These theorems are called the Dirac's theorem and the Or's theorem. Dirac's theorem says that a graph with which the number of vertices is greater than or equal to 3 or n greater than or equal to 3, and every vertex that have a degree n or the number of vertices divided by 2 or n over 2. To illustrate, we are going to use the earlier example. The number of vertices the graph has is 5, Z, Y, X, W, and V. Each of the vertex has degrees of Z 3, Y 3, X 3, W 3, and V 4. Now, since we know what is n or the number of vertices, we should compare each degree with n over v using greater than or equal to. This is how it would be. Z 3 greater than or equal to 5 over 2, Y 3 greater than or equal to 5 over 2, X 3 greater than or equal to 5 over 2, W 3 greater than or equal to 5 over 2, and V 4 greater than or equal to 5 over 2. If all the vertices satisfy the conditions, it will then be a Hamiltonian path. In this example, each vertices and their degrees satisfy the conditions. All degrees are greater than or equal to 5 over 2, thus it is an example of a Hamiltonian path. On the other hand, the Or's theorem says that a graph that has a number of vertices, or n, greater than or equal to 3, or n greater than or equal to 3, and such that the sum of degrees of every pair of non-adjacent vertices is greater than or equal to n, then it is a Hamiltonian circuit. To further discuss this, an example given earlier will be used. The number of vertices are 5, Z, X, V, W, and Y. Then, we will be getting the sum of the degrees of non-adjacent vertices. These are vertices that were not joined or connected by an edge. These pairs are Z and W with 3 plus 3 is equal to 6, and X and Y with 3 plus 3 is equal to 6. Some pairs are not mentioned anymore since they are already given. Then, the sum of these non-adjacent pairs would be compared using greater than or equal to and find out if this graph is actually a Hamiltonian circuit. Z and Y is equal to 6 greater than or equal to 5, and X and Y is equal to 6 greater than or equal to 5. The graph has Hamiltonian circuit since the sum of the adjacent pairs satisfy the condition of being greater than or equal to the number of vertices, which is 5. One of the real-life uses and applications of Hamiltonian path can be for a school service. They would want to find the best route for picking up students and going to school. That is all for today's video. Thank you so much for watching.